We're now going to discuss an application of derivatives called related rates. So the idea behind related rates is we have two quantities, two values that are changing at the same time, and we want to try to figure out a particular situation. And we're going to be doing two main things. The first thing we should always do is to sketch and label a diagram, and then we'll use some geometry to figure out what we're missing. So let's look at a couple of examples. For our first example, let's consider a spherical balloon. So we have this spherical balloon, and in addition, we're pumping air into the spherical balloon at a rate of 4 cubic centimeters per minute. And so we're trying to figure out something about this, and we want to know how fast the radius is changing. So we want to know the rate the radius is changing. In particular, we want to know whenever the diameter is 50 centimeters. So this seems like a complicated problem, but let's think about what's going on here. We drew our diagram, and we can go ahead and label things. We know the diameter is going to be 50 centimeters, and we know that this thing is increasing at a rate of 4 cubic centimeters per minute. So the volume is increasing. The second thing to do was to use geometry. Well, we have a sphere, and I just said the volume was increasing, so let's think about the volume. So the volume of a sphere, I'm going to call it V of R, is 4/3 pi r cubed. So now I have a formula that may get us started. Well, we don't actually know what the volume is. We could find the radius, but that's actually not what we need. The rate something is changing is just the derivative. So we're going to want to take the derivative. On the left, we just have V of R. On the right, I'll bring down the exponent and subtract 1. And then I'm going to multiply by r prime. I do need to use implicit differentiation here. The volume is changing at a rate of 4 cubic centimeters per minute. The radius is going to be 25 since the diameter is 50. And then we have r prime. So now, once we try to solve this, I'll end up with 1 over 625 pi is equal to r prime. So that's how fast our radius is changing whenever our diameter is 50 centimeters. Let's consider another example. This time, I'm going to consider a ladder resting along a wall. So here's my wall, the ground, and here's my ladder. We're going to say the ladder is 10 feet long, and that's not going to change. A ladder is a certain length. The bottom is initially 7 feet from the edge of the wall. However, we're pushing it up. So we're increasing at a rate of 1/2 feet per second. So we're pushing the ladder up the wall. And we want to know how fast the top of the ladder is moving up whenever we've been pushing for 12 seconds. So we want to use some geometry. We're looking at the sides of a triangle, so we're probably going to want to use the Pythagorean theorem. We'll call this side x and this side y. So we have x squared plus y squared is equal to 10 squared. Remember, 10 is not changing. The 7 at the bottom will change because we're pushing this ladder closer to the wall. But the ladder is set 10 feet, so we can go ahead and substitute that value in. When we take derivatives, we're going to use implicit differentiation, so we're going to have a 2x squared, or a 2x times x prime, and a 2y times y prime, and the derivative of a constant is 0. So now we actually have to think about what's going on. We know that x is 7. Sorry, x is not 7. So x started at 7, but we've been pushing for 12 seconds, which means we've actually increased that value by 6 feet, or decreased that value. So x is actually 1. X prime is the rate that that's changing, so 1/2. Plus 2, y prime is what we're looking for, the rate that this is changing up. However, what is y? And this is going to require a little more work, but it's not impossible. We still have a triangle. I still know the hypotenuse is 1, or is 10, and we just said that this value is 1. So we have y squared plus 1 squared is equal to 10 squared. So y is going to be equal to the square root of 99. We can then solve for y prime. This value is just 1, so minus 1 over 2 square root of 99. And this is how quickly this is changing.